Okay. Good evening, one and all. Today we move on to the last topic of our module 4, okay, which is a PN sequence generation based on asymmetric ciphers. So I hope everyone have a clear idea about what is pseudo random number and the three ways where you can able to generate the pseudo random number sequence. So one of them is PRNG, that is zero random number generators. Okay, we can able to design this PRNGs based on few asymmetric ciphers. Right. So as I said, asymmetric encryption algorithm will also be used to produce some random output. Okay, but here algorithm will be a little bit slower when compared to symmetric key algorithms because of computation complexity. But people do prefer asymmetric asymmetric cipher-based PRNGs whenever they need a short pseudo-random sequence, which will be more robust or more closer to randomness. So whenever they need a short pseudo-random bit sequence, they go with our asymmetric encryption algorithm-based PRNGs. Right. So one of the famous PRNG, which is based on our RSA algorithm. Right, I hope everyone remembers how RSA algorithm works on. Right, based on this RSA algorithm, they created a PRNG named as Mikali-Schnorr SPRNG. In the Mikali and Schnorr, both of them designed this zero random number generators based on RSA algorithms. Right, I hope everyone remember the general structure of PRNG. That is, it will get the input of a seed value, right? And you have your PRNG function. It will produce an output, and this output will be fed back as a next seed value. Right. So this is how it will produce a random sequence. Zero random sequence. Right. Similar way here, we are using this RSA algorithm to produce this PRNG. One is the seed value is called H naught, the initial value. Then we are supplying with the four different values called N, E, R, and K. Out of this N and E are nothing but our public keys. R is nothing but your private key, actually. It's a private key. And key is a value. We will see how where this value is going to play a role. So here inside this PRNG, I'm using the encryption algorithm of RSA. That is Y1 is nothing but it's not the seed value which is given. It will be risen to power E mod n. Right. So here this output which is going to be produced, it will be having a total number of K plus R number of bits. Okay. Accordingly, the seed value will be chosen to give me K plus R bits, so that we will take the K most significant bits alone and will be kept as Z1. This Z1 is nothing but your pseudo random sequence. Pseudo random number. Maybe this is the first number, right? And the R number of bits, okay, R most significant bits will be taken as X1 and it will be given as an input for the second iteration. So the seed value for second iteration is nothing but your X1. This fed back from the previous output, and same values of n, e, r, and k will be again fed here. Then they take the second iteration output, and this will be my second number. This will be third, and goes on. So this iteration will be repeated until the required length of sequence have been obtained for the PN sequence. Right. So this is how your RSA based serial random number works on. Then what I just defined, it is explained here. And these are the conditions, how they are choosing the parameters n, e, r, and k. And the n will be chosen in the same way how we will be choosing for our RSA algorithm. That is by choosing two prime numbers p and q, and we'll be multiplying to get n. Okay, and e will be chosen in such a way that it belongs to 1 greater than 1 less than phi of n. The same conditions which only we just used for this one. Right. Whereas here, this r into e should be greater than or equal to 2n. This ensures that what can you say? The complexity doesn't increase more. Okay, just for that purpose, they are using this one. And mostly the k and r will be in multiples of 8. Why? In the sense, Suppose if you need a PN sequence in binary, right, like in bits ones and zeros. So if you are going with multiples of 8 means you can able to convert them into 8 bits, or from here you can able to convert them to bytes and other stuff. Okay. So that's why they'll be you going with this one, and this R plus K is something with the total size of the output of the PN sequence, yeah, right? And K will be always greater than or equal to 8. So this is the based on these conditions only they'll be choosing the values of N, E, R, and K to supply for a PRNG based on RSA algorithm. And then there is also PRNG based on elliptic curve cryptography. I'm not going to discuss this one in detail because it is somewhat very lengthy and we don't have enough information on this one because it is developed by US National Security Agency. Okay. And it is most complex PRNG sequence ever existing. It uses dual elliptic curve PRNG or DEC PRNG, dual elliptic curve PRNG. Okay, it has some issues on its security and inefficiency also. So here they will be using 2 points, and addition of these 2 points will let me know. Let me give the output for the PN sequence. Right. So with this, we are concluding our module 4. I hope the serial random sequence is clear. If anyone have any doubt in this PRNG, you can ask me now. Right. Okay. With this one clear, we will move on to our next module. Okay, so with this, we are concluding our fourth module. In fourth module, we have only few topics, starting from your Diffie-Hellman key exchange. Then we have discussed about L-Gamal, then ECC based L-Gamal system. Right. 1 second. Right. Now we move on to our module 5. So module 5 is titled as data integrity. Can anyone tell what are these symbols denote? Can anyone tell why? What are these and why it is kept here? Any idea what are these symbols denote? You can use chatbots or you can unmute and tell.
Cryptocurrency.
Yes, cryptocurrencies. Perfect. Yeah, so this is your famous bitcoins. Then we have Ethereum, Tether, other kind of currencies also there. Right. So what does these cryptocurrencies are going to do with this data integrity? We'll see. So data integrity, in this we are going to discuss majorly these two functions called cryptographic hash functions, which is the backbone for our cryptocurrencies as well as for blockchain technology, and message authentication code, which is nothing but like an enhanced version of a cryptographic hash function. Like someone like how we had an enhanced version of DES as AES. Similar way, hash functions enhanced version is MAC, that is message authentication codes. But in this case, we don't have any drawbacks on hash functions. In order to increase the functionality of a hash function, they have upgraded as message authentication codes. Right. So to start off with cryptographic hash functions, we should know what do you mean by message integrity first. Then what are design criteria to go with the cryptographic hash function. Then what do you mean by iterated hash function? Because this is the base. How we have our product ciphers and fiasco ciphers, which is the base for all the block ciphers. Similar way, here we have iterated hash function. Then we introduced to a new term called compression function, and we will see two different groups of compression function. Then here in this part, we are going to discuss one of the most famous hashing function which is still in use, that is called message digest family. It has different versions. In this, we'll be discussing MD4 in detail, and we'll see how this MD4 is upgraded as MD5, which is used till date, and SHA-512 called as secure hash algorithm. Okay, SHA-512, which is also in use. Then there's another hashing algorithm called Whirlpool. Okay, so we'll be discussing all these three algorithms. Before that, we'll be discussing what what do you mean by this integrity and other stuff, right? So before moving into this one, there is a small question from my side from module 1. Can anyone able to tell what are the 3 security goals which we came across? Because of these security goals only cryptography came into existence. The 3 security goals. Can anyone tell? And for information, data integrity,
Data privacy, data authenticity, and data integrity, sir.
okay, data privacy, okay, it's you have kept a new name.
Data
Okay.
confidentiality,
Yes, yes,
integrity, and availability.
yes. Okay. Yeah, perfect. So 3 goals are confidentiality, integrity, and availability. Right. So till module 4, whatever we discuss, okay, those algorithms and all the stuff, and especially in 3 and 4, okay, because second is a base for our mathematical base for everything. Module 3 and 4 gave us entire algorithms or ways which can be used to provide data confidentiality around. Okay, from this module onwards, we will see where we need integrity because there are certain applications because what we just studied so far provided secrecy to my data, thereby giving me the confidentiality. But we didn't see anything about integrity here, data integrity. Because there are certain occasions where we need integrity more than secrecy. Can anyone tell any examples? That is, I hope everyone knows what is message integrity. Okay, to brush up, I'll just say message integrity in the sense whatever the data which has been transmitted, it should come unaltered to receiver, right? Unaltered in sense, even if suppose if you are using any cryptographic algorithm, okay, if some attacker is attacking and they are sending 64-bit and you are getting 64-bit. But what is the guarantee that these 64 bits are exactly sent by that particular user or not? Especially if you see in man in the middle attack, we don't have the data integrity maintained. You have a transmitter here, I have a receiver, he is sending a data. For example, he is sending 10 bits and you are receiving 10 bits. Okay. What is a guarantee that these 10 bits are alone sent here? What is the guarantee? That is called message integrity. Right. So can anyone tell any example where we no need secrecy but we need integrity? Any example? Just think. Okay, think in such a way that any value display or any message displayed. Okay. No need of secrecy, but integrity is major thing. Okay, I will tell an example, basic example. We'll go with our university itself, PAT. Right. So you are registering for a subjects. Okay. But and for each subject you are selecting a slot. For example, cryptography you are taken G2 slot, right? And in your timetable it is getting displayed. I mean that you have got cryptography, but the slot is changed. Assume that you have a slot. You are thinking that you got G2. Okay, but only you are checking that okay, I got cryptography, but there is no okay. I'm not going to confuse with this one. I'll go with the basic thing. Okay, with the document and fingerprint example. Okay, the wills. Okay, nowadays grandparents, everyone are writing a will, right? So this will be becoming. It will gain its power after the period of the particular person got passed away, right? So here everyone will can able to read the will, but no one is allowed to change the will. Okay, not to preserve the integrity of the document only. Okay, either they'll use a signature or they use a fingerprint. So whenever mostly they go for fingerprint because signature they can able to replicate, but fingerprint we can't able to replicate. Assuming that we don't involve any technology or any James Bond stuff, right? Simply assuming there is a will document, they are writing something, and they'll be providing a fingerprint here, right? So this is the best way to preserve integrity of a data. That is, you are writing a document and you are using a fingerprint. So no one can able to replicate the document with their own data, claiming it to be the which is actually originally written. Okay, so if Alice needs to be sure that content of her document will not be changed, she has to put her fingerprint at the bottom of the document or signature if it is not a replicable one. Right. So this document, anyone can are allowed to read the data, but no one is allowed to change the data. Right. So this is the basis for our hash function. Right. I hope everyone have a clear idea about integrity now. Right. What is message integrity and what is the difference between data integrity and data confidentiality? If it is clear, raise your hand. If anyone have any doubt or confusion between data integrity and data confidentiality, you can ask. Right. Now we'll compare this message. I mean, whatever I just saw now, we'll compare it with message digest. What is message and message digest? Where is hash function come into play? And we can able to compare exactly with the document and fingerprint pair. So if this is our real-time example we just saw, we'll have a document and we'll be having a fingerprint with ensures data integrity. Okay. So in hash function, this document is termed as message and this fingerprint is termed as digest. And this altogether is called as message digest pair. Right. So this is the synonymous. Wherever in real world we are using document, it will be called as message in our cryptographic point of view, and the fingerprint is termed as digest. So whenever you have a message or a document, and if you give this document as input to the hash function, like how we have encryption algorithm and decryption algorithm, here we have a hash function. Okay, this hash function will produce a digest value or a value. Assume that it's a value, but this is not like in real world you'll be having a document and you will be putting a fingerprint. Whereas if you compare this with our cryptographic technique, where you'll be using a hash function based on the message which you are giving, it will produce me an output called message digest. This digest is also called as hash value. It has two names, message digest or hash. Mostly in our discussion, I'll be using it as a hash value as a name and this one as a message. And this is how your hash function works on. So what is the difference here? If you see a document fingerprint, a document and fingerprint pair and a message and digest pair. Okay. Major difference is nothing but document and fingerprint are physically linked together. Right. Because on the document you'll be signing. Whereas in our message and message digest pair, they are unlinked, they are separated. And one more thing, this message digest has to be kept very secret in this. We will see how this can be kept secret. Okay. And for one thing, for example, assume that this is a message, like this is from a cryptography class. This is module 1 document. Okay, I'm just giving to you by hashing. It will produce a value. Assume that it produces 767. Some value. This is a value which will be produced only for this module 1 document. Suppose I'm the same person. Okay, Mugelan is going to upload second module data using the same hash function. It will give me another value. I may be the same person, but if you compare it the real time, if I'm signing all this module 1, module 2, I'll be using the same signature here. Whereas here, the signature, or the digest value will be keep on changing with respect to the change of input, not with respect to person. If one person is going to transmit multiple messages, each and every messages will have their own digest value. Okay. You'll see these things in the upcoming slides. Okay, so message digest needs to be safe from any change because this message digest secrecy is most important thing for this data integrity. Okay, so to keep this message digest very safe only, nowadays we people are using this blockchain technology. And for keeping this safe, you are getting rewarded as your cryptocurrency. This is a basic thing and there are other stuff. We are not going to discuss those things here. Okay. So how the checking of integrity will be done? Okay, hash function is not like our encryption algorithm where we'll be having a decryption part at the receiver end. Here hash function or non-invertible functions. So you can't able to find the inverse of hash functions here anywhere. Okay. So if you have a message, assume this is at the receiver end. Okay. In receiver end, you are receiving the message, okay, and you are hashing that message, and you already have the original digest value which you already got. That is, at the from the transmitter end, you got the digest value previously itself with you, and you are using the same hash function at the receiver end, and you are producing another digest value, and you will check whether this digest value and the digest value which I received from the transmitter both are same or not. Okay, if both are same, then the message is not changed. If there is a change, then message is changed, then it will be discarded. Right. So it's like using the same function at both the end to check whether they're producing the same output for the hash function with a particular message. Clear, guys, how this hash function or checking of integrity is happening? It's clear. Raise your hand if you have doubt. Okay, someone used chat window. So is hash value always numerical? I just said for example, it need not be mandatory to be a numerical, but in our real world scenarios, mostly it will be used as a integer values only, or sometimes hexadecimal values. But it is not a mandatory one. It's up to our wish. So I hope this data integrity part, is it clear, guys? How they are checking? Okay. Now we move on to cryptographic hash function criteria. I want everyone to listen to these three criteria very carefully, because the small confusion will be there always, because in the books also they mentioned that the confusion may occur, but I try to keep it as simple as possible to explain these three design criteria. First one is called pre-image resistance, then second pre-image resistance, and collision resistance. And this collision resistance is a subset of second pre-image resistance. It's like inside this criteria only this criteria lies. We'll see. So first one, pre-image resistance. That is based on these criteria only you have to design your hash function, okay, or the entire hashing system. Okay. What this property is trying to do in sense, that is, if you are able to create a hash function, okay, such that it should be computationally very hard to reverse that hash function. Okay. In other words, if you want to put, if you have a hash function called h, which will produce me a hash value called z. Okay, whenever you are providing a input called h, that is, you have a hash function h. One second. You have a hash function h. If for the input x, I am going to get output as z. Right. So this is your hash function. So it should be a very difficult process for the attacker to find any other input value. Okay, any other input value. For example, he is using another value called y. Okay. So if you substitute hash of y, it should not give me the same hash value. That is, this attacker will, when he will do this kind of attack in the sense, if he has only the knowledge about the hash value alone. Okay, so this property protects against an attacker who only has the hash value. That is, he has the knowledge of set. So what he will try to do in sense, he will try to create his own hash function with some input value on his own, such that he is going to get the same value here. Okay, so if your hashing function is going to satisfy this property, then this is it should be a computation hard for to find the reverse of the hash function, right? So for example, this is how exactly it will look like. That is, you have having a message and you are hashing, and this is y is nothing but output you got h of f. So in this example, they kept y as a hash value, right? So here they are sending to Bob. In the middle, he is hacking. Okay, he is having the knowledge of the hash value y. Now he is trying to find another value for message such that he can able to find the original value of y. I mean, so he can produce the original value of y again. If he can able to produce that original value of y, then he can able to transmit his message here to Bob, so that Bob, while checking, he will get the same hash value, right? This is pre-image resistance. Now we move on to second pre-image resistance. So here, if you are given the input and its hash value, then it should be hard to find a different input with the same hash value. That is, in this case, the attacker will have knowledge of both input value and its hash value. Previous, first pre-image resistance, this one simple pre-image resistance, he has only the knowledge of hash value alone. Whereas in second pre-image resistance, he has knowledge of both hash value as well as the input value. That is, he has knowledge of message also, right? So he has a hash function. For an input x, he produces a value called h of x. Okay, now he has to find another input value y such that h of y should be equal to h of x. Okay, because now he has a knowledge of input also. That's a major difference here. So generally how this will happen in the sense, the transmission originally, since first the message will be hashed and they will concat this message and the hash value into single packet as a single packet, and this will be transmitted to the intended user. So attacker is going to now get the packet, and he is opening the packet. Now he has a hash value to his knowledge, and he also has the information on message, but he doesn't know how the hash function works on. Now he has to find another message value m dash such that if he hash m dash with h, he should get the same hash value of y. Okay, if this happens, means then you have failed second pre-image resistance. So you have to design your hashing function such that this kind of action should not be happening here. Is it clear, guys, regarding the pre-image resistance and second pre-image resistance? If it is clear, kindly raise your hand.
Excuse me, sir. Can you explain the major difference, like for the pre-image, the first pre-image resistance? In this also, like we have to prevent the person from having a different hash value, getting the same hash value with a different input, right?
Yes, yes, yes. But here
So,
in this case, he doesn't have the knowledge of this message. So here he will be keep on choosing different message values to get the hash value. Suppose he has the knowledge of a message, means his search for this m dash will be somewhat easier. That is happening in the second scenario. One second.
okay, so that's the only difference, right?
Yes, yeah,
Like,
yeah.
but how does it like if he knows the input value or if he doesn't know the value, if he's gonna use like a trial and like some other method to find the new input value which gets the same hash, it will still be the same process, like the same difficulty process. Like how would knowing the input help
For example,
the other?
okay, in the previous example, he doesn't have the knowledge of message. Assume that the message is made up of like 64 bits. Okay. So in previous thing, he doesn't have this knowledge of 64 bits. So he'll be trying from giving an input of 1 bit, 2 bit or a 3 bit, and you have to try in all the different sizes, because one unique property of hash function in the sense, whatever the size of input you maybe give. Okay, even you can start from 1 bit and you can go to 1024 bits. Okay, this is a unique property of hash function. Whatever the size you're going to give for the hash function, this will give me a fixed length output. If it is going to give only 3-bit output, means it will give 3-bit output even if you give 1 bit as input, or even if you give 1024 bit. That is a unique property of hash function. So whereas in this case, if he has a knowledge of the input, so input is 64 bits. So for whenever you give 64 bit, he is giving some value. Assume that is giving like SSL 471. That's for a no, example purpose. So he has a knowledge that size 64 bit is enough for us. Or assume that it is like a 10 digit or integer kind of thing. So 10 digit is enough for me, means he will try only all the combinations of 10 digit m dashes. So this is like helping the person with extra knowledge, if his attackers can able to get the message. Whereas in this case, it's very difficult for him. Even if you go with the less computationally complex hash function. Whereas in second pre-image resistance, you have to make a more robust hash function such that even he has knowledge of this message, and from this he can able to get the length of this message also. he can able to get this hash function directly. Sorry, hash value directly.
Okay, sir. Got it.
Simple knowledge means, I mean, pre-image resistance, he has knowledge only about the hash value, whereas, but his motive is same. He has to get another input value to get another copy of Y. But in first case, he has knowledge of only hash value. In second case, he has a knowledge of both Y and M. That's all. Is it clear,
Okay.
Kashish?
Yes, sir. Got it.
Now we move on to collision resistance. Okay, actually, this is like a subset of a pre-image resistance. What example I just now said to explain to Kash is the same thing. Here in collision resistance, what the attacker will do in the sense, he will try to find, okay, as I said, the hash function is going to come use some function to get a fixed hash length. It should be impossible, okay, for hash function not to have collision. Collision in the sense, like if you're getting hash function hash value of different size, okay, so the different size should not come because it's going to give a fixed hash length. That is a property of hash function. So here I'll just explain from here. So he will be using the length of the message, whatever I just said previously. Okay, what he will do in the sense, in this case, he has knowledge of both message and hash value, but here he is keenly interested in changing the length of the message. So especially in this case, if you say it is made of 64 bits, what he will try to do in sense, here either he will try to go with like 48 bits, lesser bits, or 256 bits of message, different length of message. He will try to change the length of the message to produce the same hash value. In this case, he will concentrate only on the length, not on the data. Whereas in second pre-image resistance, he may get the input from 64 bits, but he will also try to give the same length of message as the input there. Whereas in M dash here, he'll choose different length. That's why if you see, you can able, if you put them in a Venn diagram kind of thing, pre-image resistance and second pre-image resistance are almost same. The common point of pre-image resistance and second pre-image resistance nothing but the knowledge of hash value. Second pre-image resistance has additional knowledge of the message M. Collision resistant, he knows the length of the message also, and he will try to change the length of the message with another M dash. Is it clear, guys, or I'm confusing you people? If it is clear, raise your hand, because collision resistance, simple logic, he is trying to change the length of the message. Right. Okay. I think I'll just go with the applications of cryptographic hash function. With that, I will conclude this today's session. This will help you to understand how this cryptographic hash functions works on. Okay. So this is the first example. This is the first scenario. In first scenario, I want to maintain both data integrity as well as data confidentiality. That's my this application requires both confidentiality and integrity. So this is the message I got. What I'm doing, since I'm taking the message directly here, but I'm hashing the message, I'm getting the hash value, that is h of m. In this step, concatenating both of them, that is I'm putting single bots also. It is not being. No. That is, you have your h of m is y and you have the message, both of them put in a single box. Then I'm performing an encryption algorithm. So at this point, at this point, I have introduced my data integrity point. At this point, I introduced my data confidentiality. So while transmitting, I'm encrypted using a key called K, where I have message and h of m, that is hash value, both are kept intact. So at the reception end, first I will decrypt. Once I decrypt, I will getting the raw packet of message and h of m. I will take m unknown separately. I will perform the same hash and I will compare whether the h of m produced at the receiver end is exactly same as whatever I just got in this part. If both are same, then the data integrity as well as confidentiality is maintained here. Is it clear, guys? The first application? If it is clear, kindly raise your hand. First, if you're clear with this first application, then I move on to next two, right? So in this second one, B part, here I don't care about the confidentiality of a message, but I care about the confidentiality of my hash value here. So here data integrity is maintained and hash values confidentiality is also maintained. So message is taken, they took the hash value, they encrypting the hash value because they want to keep the hash value very confidential. So and they have a doubt on the hash function, that is the attacker may can able to manipulate. So they are encrypting this hash value alone and they are concatenating here. So here in concatenation, the message is kept raw. So anyone who is having the access to this public channel can able to read the message, but they won't have the knowledge about the hash value here. Because this is encrypted as using key and h of m is the message here. So once it is received, they will hash the thing and will keep getting the h of m here. And here, what are the encryption algorithm? If you are going with symmetric key cryptography, the same key will be used here. And for this key exchange, they may use any key exchange algorithm like Diffie-Hellman or anything, and they can able to decrypt and they can able to compare the hash values. Right. And in this one, the third one, okay, they want to make it more sophisticated. Okay, that is secrecy. They want to introduce. Right. So what here they are doing in the sense, the message is taken and it is kept separately, and the message is now appended with a secret value called S, and this S is known to both transmitter and receiver. Okay, so what they're doing, since the message plus the secret value is taken, the both the values are now hashed, right? And it is appended here. Right. At the receiver end, okay, anyone who have the knowledge of message M, even if they try to find h of M, they won't get the same value because here a secret value called S is added with message here. And this message is taken to the receiver end and it S is added and they get the h of M, I mean h of M plus S, right? And it will be compared with this value, both are same, then integrity is maintained. And the last one is a most sophisticated system where you can able to, we are challenging the attacker. You can't do anything because you introduced all the techniques which you have learned into this one. That is, the message is taken. Okay, you are adding the secret value. You are hashing. Okay, you got h of m and s, and again it is appended with this message plus hash value of message and s, and this entire packet is now encrypted and it is transmitted. So first a decryption to get the raw packet, then addition of s with the message, then you're getting h of ms, and this is again compared to this one. So these are the four mostly used application, and using hashing function and cryptographic algorithm, it's open to all. You can think any other method also to make it more robust. Right. So okay, I think with this I will wrap up today's session. And next class we'll start with different ways where this properties can be applied. Right. So anyone have any doubt in this today's discussion regarding applications or the properties or regarding the message integrity, anything, you can ask me now. If it is clear, kindly raise your hand so that I will wrap up the session.
Excuse me, sir.
Yes, sir.
For collision and second pre-image,
Yeah.
in collision, we are changing the size of the length of the message, right? Like
We are
that
not
is being
changing the attacker. The attacker will try to change.
yeah. So like and for the second pre-image also, we are like the attacker will be doing the same thing, right? He'll be
No. For your example, what I said in sense, he will have the knowledge of this one, so that it will be easy for him to find another message m dash of same length. Without
okay
knowledge
of
of this
same
length,
length.
yeah,
Okay,
same length.
okay.
Anyone have any more doubts? Thank you, Kashish. And also, Kashish, suppose like change of length and sense, even he can able to take the original message and he can able to drop few bits and reduce the bits, and he'll try to find a new hash function also to give the same hash value also. Okay, so such kind of things will be done by attackers.
Okay, so this when you change the size, the length of the bits, that will fall under collision then.
Yes, yes, yes. Whenever you are touching the length of the message, it comes under the collision resistance property.
Okay, so sir, like for in this example, second pre-image, if the message is of 64 bits, then the different value that the attacker will be looking for is like will be of 64 bit only.
Yes, yes, yes.
Okay.
I assume that the people are clear. Okay, then we will wrap up, guys. Thank you.
Thank you, sir.
Thank you, sir.